Welcome.
Thank you, and thanks for having me. So, can everybody hear me okay? Okay. As mentioned, I just moved to Liverpool, so I basically stayed in Göttingen before and just moved there, so I kind of put the 4 most famous Scousers on there to show the way that I just followed. So, and here's a brief outline of what I'm going to talk to you about. So I want to introduce you to globular clusters and mainly be talking about what I'm most interested in, which is their kinematics. And in the middle part of my talk, I want to highlight some of the observational problems that we're actually currently facing and how we are going to solve them to study all these questions that we currently have about globular clusters. And one kind of take-away message that I would just want to put at the beginning of my talk is that sometimes it's good to relax, and since we're kind of approaching the end of the conference, it's maybe also be a good time. But what keeps globular clusters interesting to us, especially looking at their dynamics, is that they know how to relax, basically, and I hope I can convince you of that. So what's a globular cluster? Well, probably most of you know that globular clusters are massive star clusters that we basically find in all massive galaxies that we know of. And for instance, in the Milky Way, we know of the order of 150 globular clusters. And there's a few even being still discovered that are hidden behind clouds of dust and so on. And what's kind of the general property that everybody agrees on concerning globular clusters, it's that they're basically very old. So they belong to the oldest objects for which we can determine reliable masses in the universe. And if you look at the color magnitude diagram of a globular cluster, like in this case 47 Tax, so the guy that I just showed you here, one of the most massive globular clusters in the Milky Way, and compare this to models of stellar evolution, you arrive at an age of 10 gigayears or even older. Recent discoveries have shown us that globular clusters are actually more complex than we once thought. Because if you look at a modern day HST color magnitude diagram, which basically shows you UV magnitude against UV minus infrared color, you see that this color magnitude diagram, which looked pretty simple a while ago, actually splits up into various populations. And there's a basic agreement that these populations, which are characterized by subtle differences in their chemical abundances, tell us something about globular clusters formed. However, there's been several theories proposed to explain this, and basically I think it's fair to say that none of those theories so far agrees with all the measurements that we have. So it's still a mystery basically how exactly globular clusters formed. But what I want to tell you more about is the kinematics that we find inside of globular clusters. So of course globular clusters have mass, so the stars must move in them, otherwise they would just collapse. And since globular clusters are basically spherical objects, rotation is probably not the governing kinematic property that defines them, but it's more that the globular cluster is characterized by the arbitrary or the unordered motions of the star through it. So in a way you can think of a globular cluster behaving as kind of an idealized gas of stars moving around with a certain temperature. And this idea of treating a globular cluster basically as a gas of stars has some history, since the earliest models that were proposed to explain globular cluster kinematics were those King models, which exactly treat a globular cluster as a gas of stars. And you consider the relative energy of a star, so the gravitational potential that a star experiences in the cluster, reduced by its kinetic energy. And then you consider that if the kinetic energy is higher than the gravitational potential, the star is basically unbound and leaves the cluster. But if it's lower than the gravitational potential, the star likes as if it would be in an isothermal sphere. And if you do the mass that's behind this, and then think of how would the density profile of a globular cluster look like, so basically plotting surface density or the 3D density against the radius, then you basically find these curves predicted that I show here as solid lines. And if you compare these two models for different globular clusters, then you actually find a very good agreement. And if you go one step further and also look at kinematics, then you also find that the kinematic measurements that we have can also be explained by these models. So what you often see is that you have a plateau in the center of the globular cluster. So what's plotted here is again velocity dispersion against the distance to the cluster center, and you basically have a plateau in the center of the cluster and then a steady decline towards the outskirts of the globular cluster. So this is I think a very nice result that we can basically explain the global kinematics of globular clusters with those simple models. What we also find when comparing to those models is that basically the gravitational potential that we need to explain the kinematics of clusters can be described as we expected from stellar evolution, so there's no need to invoke something like dark matter or so. And if you look at a kind of our state-of-the-art view of globular clusters, we have a variety of sophisticated models available which we can use to describe them. Analytical model, n-body models, which I show here from a recent publication by Baumgart in 2017, which basically predicts the surface brightness of the cluster and the velocity dispersion profile very accurately. So you see that we're basically at a state where we can describe the kinematics to better than 1 kilometer per second. So this is very nice, but why do we then still care about globular cluster dynamics? And the answer to this is basically because they evolve. And to explain this, we have to think that the globular cluster, in the center of a globular cluster, we have a core density which is basically of the order of 1,000 stars per cubic parsec. So it's several orders of magnitude higher than in the solar neighborhood. And this leads to the fact that we have frequent gravitational encounters between the different stars. And the gravitational encounters, they have various effects. For instance, they will alter, of course, the orbits of the stars. They can destroy binaries, but they can also form new binaries. And they lead to an effect which is called energy equipartition, which means that if you have an encounter between two stars with different masses, then the encounter tends to equalize the energy of the two stars, which means that on average, you'll decelerate the more massive star and accelerate the less massive star. And this leads to two effects that I'll mention in more detail in the following, which are mass segregation and core collapse. So let's start with the first one. I was talking about relaxation, so I want to introduce first some kind of the quantity with which we describe the evolution of a globular cluster, which is the relaxation time, which is basically the time during which an average star will significantly change his orbit because of encounters with other stars. And it's governed by this rather complicated formula, including the radius of the stellar orbit, its velocity, and the number of stars in the cluster. And if you do the math behind it, you find that the relaxation times for clusters in the cores are at the half-light radii, so the radii containing 50% of the light of the cluster. They're basically shorter than the lifetimes of globular cluster. So these effects of relaxation should be visible. And we can actually view them, look at them, as I'll show you in the following. So I mentioned core collapse before. What's the idea behind core collapse? Well, I mentioned the effect of energy equipartition, so that if we have encounters, the more massive stars get decelerated. Now, if we have decelerated stars, they'll sink to the center of the cluster, where they will accelerate again. This means we have two effects. The center of the globular cluster, on the one hand, gets denser, and also its velocity dispersion increases. And this basically leads to an instability, which is called core collapse, because the core basically starts to collapse and get denser. And at some point, this evolution is finally halted by binary stars. But we can actually see the traces of it in the velocity, in the surface brightness profiles of the globular clusters. And here I've shown one work by two people here from the institute, so Evan Oyola and Karl Gebhardt, investigated the surface brightness profiles of several globular clusters using the HST, using HST imaging, and you see here that, for instance, 47 TAC has still a very nicely visible core, so basically the density stays constant in the center, but if you move to a globular cluster like NGC 6293, the density increases steeply towards the center of the cluster, and this is exactly what we think is an evidence for that this cluster has undergone core collapse. Now, if we see the effects of core collapse, we should also see the effects of mass segregation. So more massive stars being more frequent in the center than in the outskirts of the cluster. The problem is this is observationally very challenging because we basically have to count stars along the main sequence, because if you look at how the mass of the stars behave in a globular cluster, basically the giants all have the same mass. And if you want to look at different stellar masses, you have to go down the main sequence. And if you count your stars, you of course have to be very careful about getting the completeness right at different magnitudes. And this is very tricky, but the launch of the Hubble Space Telescope was a big step forward in this progress. And to show you one example, this is NGC 6397, a very well-evolved globular cluster that is supposed to have undergone core collapse. And if you look at the mass function at two different radii, so once in the center, where you see that basically more massive stars are more frequent than less massive stars, and if you go to the outskirts, so at a radius of 4.5 arc minutes to the center, you see that the less massive stars are more frequent than the more massive stars. And this is exactly this effect of mass segregation that we want to look at. Now, if we can observe mass segregation, can we also observe energy equipartition, so that more massive stars move slower on average than less massive stars? And this actually gets more tricky, because then we do not only need to count stars, but we also need to measure their velocities. And the typical way of measuring velocities is you take a spectrum. But this is actually observationally much more challenging. And to illustrate this, I show you here the center of a globular cluster, M13. And my question would be, can you guess how many stars of those that we see here have spectra so that we can get their velocities? Any guesses?
0.
0, 3. 3 is actually quite close. So there's 4 stars. There's 4 stars with spectra available. And if you look at which stars those are, it's mainly the brightest giants, and they basically all have the same mass. So we have a real problem here. But there's all these stars, and we can only get spectra of 4, so that's pretty disappointing. What's the problem actually here? Well, if you observe M13 from the ground, you have to bear with seeing. So this was an HST image. If you observe it from the ground, it looks a bit more messy. And the problem is now, if you want to get spectra, where do you place your fiber or your slit? Well, this star is probably very easy. You can get a clean spectrum of this one. Let's take this one. There you already have contamination from a neighbor. Or if you want to get a faint one, you'll surely have contamination from brighter neighbors. So we have a real issue here. And the advantage of imaging is just that we have all the spatial information that we lose when we do spectroscopy. And we can use this to actually deblend the sources, even if they overlap, and study them in detail. I want to briefly show you the idea behind this approach, which has been very successful for imaging. So the idea is to recover the point spread function of a star from the data. So the point spread function basically describes the intensity profile that a star will leave on the detector. And now let's assume we have one star, and then we have a second star that basically disturbs it. Now, if we have the profile of the point spread function, we can basically use this information to scale the brightness of both stars such that we basically get a best fit to this combined profile, and then we will have the images of those stars separated. So that's the idea behind those crowded field photometry tools like Deophot that have been very successful, been used in imaging data. but if imaging works so great on globular cluster centers, why do we have to care about spectroscopy at all? I mean, we could just try and get along with imaging, because nowadays there's proper motion studies available of globular cluster centers. So the idea behind proper motion studies is that basically you observe a cluster, then wait a couple of years and observe it again. And if you do your measurements precisely enough, then you can actually view the small displacements of the stars on the sky. And to give you an idea of what accuracy is required, assume you have the typical distance of a globular cluster is something like 10 kiloparsecs. And then you have a velocity dispersion which is of the order of 10 kilometers per second. And if you do the math, then you arrive at a displacement on your detector of the order of 0.2 milliarc seconds per year. So it's very, very small, but with instruments like the Hubble Space Telescope or soon with Gaia, that's actually possible these days. And to give you just one example, this is a study with HST by Anderson and van der Marel, where they looked at Omega Centauri using 3 epochs of data gathered over 4 years. And you can see here that they were able to measure the displacement of the stars along the X and Y axis of the detector. And so HST has actually been quite successful, for instance, in looking at the mass-resolved kinematics of, for example, M15 in this study by Bellini et al., and maybe concentrate on the lower panel of this bit complicated figure, where you basically have here the main sequence of the globular cluster, and then different colors correspond to different bins in brightness, so different bins also in stellar mass. And if you then plot the radial distribution, the radial shape of the velocity dispersion profile, and split this up into the various masses, then you see that the lowest mass bin actually has the highest velocity dispersion here, and the highest mass bin has the lowest velocity dispersion. And this is exactly this energy equipartition effect that we're supposed to see. So why should we care about spectroscopy? And in the rest of this talk, I want to convince you that spectroscopy is actually not dead, despite of these great advances that we've seen with proper motions. I think we just need to turn our spectra into images. And there's 2 ways of doing this, Fabry-Perot spectroscopy and the one I want to concentrate on, which is integral field spectroscopy. So the idea that you take an image and in each pixel or spexel of the image you have a complete spectrum. And the idea that basically gave me my PhD was that we should be able to do the same analysis that they do in imaging on integral field cubes. So, and we actually have an advantage if we do our integral field observation on some field where there's HST data already available. We actually don't have to search for the stars, but we already know where they are. So we can identify the positions of the stars in our integral field data cubes. And once we have the positions of the stars, we can use the information to try and recover the point spread function in our data cubes as a function of wavelengths. For instance, I show you here from this data that we took with the PMAS integral field spectrograph at the Calar Alto 3.5 meter telescope, how we recovered the full width half max of the point spread function as a function of the wavelengths for our observations. Now, if we have both of these information, the positions and the point spread function of our data, we use this information and basically deblend all of the spectra of all the bright stars that we can still resolve. And here I show you 4 example spectra, and to show you that it actually works, let's zoom into the center of this cluster where we have this bright star for which we get a very nice and high resolution spectrum. But for instance, even this small star that's very much blended with this star, we still get a decent spectrum of it. And also if you have blends of equally bright stars like those 2 here, we still can get their spectra. And you see that one of them has very broad lines, as is typical for a horizontal branch star, and the other one has narrow lines as typical for a red giant star. And that agrees actually to their position in the color magnitude diagram. So it actually seems to work quite nicely. And before our study, there were measurements for 4 stars, and we actually pushed this to over 100, which I think it's quite a success, but is it really worth the efforts? I mean, we have now 100 stars, and with HST they can get more than 1,000 stars. But I think, yes, it's still worth the effort. We just need better instruments. And one instrument that has grown very close to my heart over the last years is the MUSE integral field spectrograph, which was deployed a while ago at the ESO Very Large Telescope. And I had the pleasure of being involved in the consortium that built it. And in a nutshell, MUSE is a panoramic integral field spectrograph, which basically combines a 1 arc-minute field of view with a 0.2 arc-second spatial sampling. And if you do the math, that's 300 by 300 spectra in each observation. So if it's even a factor of 3 larger than this great virus spectrograph that you're currently building at McDonald's Observatory. It also covers a very wide wavelength range at a reasonable spectral resolution. And why MUSE is so great for the stuff that I'm doing is basically, if you compare this to the data that I had available during my PhD, it looks like this. And put it on the same scale, then it's like this. And this was something like 5 nights of observations, and this was 5 hours. So you immediately see how much more we can learn from this data than from this data. Does the extraction also work on this more complicated MUSE data? Actually does. So I like to show this example where we have 2 stars that even on the HST data are heavily blended, but you actually see that it's 2 stars because they have 2 different diffraction spikes here. And of course, they're also very much blended on the MUSE data, which has a lower spatial resolution. But if we do the extraction, we get a nice spectrum for a red giant star with a narrow calcium triplet here for this star, which actually is a red giant. And for the other star, we get the broad Paschen series here in the red. And this is actually also what we expect for a horizontal branch star. So this extraction, it also works for the MUSE data. And if we looked at the whole mosaic that we observed for this globular cluster, NGC 6397, this is a color magnitude diagram of all the spectra for which we extracted stars. So in total, we had of the order of 12,000 stars in our sample, for which we extracted 19,000 spectra. So the number of spectra is larger because we observed several fields twice. And this back then was the largest spectroscopic sample that was available for any galactic globular cluster. And basically you see that we almost cover or get spectra for almost the entire color magnitude diagram of the cluster. And the mass range that we covered was something like 0.4 to 0.8 solar masses. So that actually enables us to look for mass resolved kinematics. And this is the result that we got from this data. So showing the velocity dispersion as a function of distance to the cluster center. And if you look to the center, you see that we start observing that the highest mass bin here, shown in red, has the lowest velocity dispersion. So we're getting there that we are able to observe mass-dependent kinematics also with spectroscopy from the ground. And we were quite happy with this result, so we started to do a bigger survey of 25 globular clusters. And this is my mosaic of basically collapsing the data cubes along the spectral direction and then making color images of those. So this is a mosaic of 25 globular clusters that we observed, including also the famous cases like 47 TAC and Omega Centauri. And in total so far, so the observations are still ongoing, but we already gathered spectra for more than 200,000 stars, and in total we gathered something like 1 million spectra currently. So it's really becoming a big survey. And there's various science cases behind it, and I want to concentrate on 2 of those, namely kinematics and binary stars in the following. What you see here on the right is the number of spectra, how it splits up into signal-to-noise ratios. So of course, if you try to get a spectra for every star that you can observe, you also end up with a number of low signal-to-noise spectra. But that's just how it is. And one thing I first want to talk to you about is, do globular clusters rotate? I told you in the beginning of the talk that they don't, but that's actually not quite true. And there have been several studies showing that there's kind of a rotation does play a role in globular clusters. For instance, there was a study by Glenn van der Ven et al. On Omega Centauri, where they actually studied in great detail the 3D information they had from both proper motions and radial velocities to show that this cluster had a very strong rotation field. And one study that has been done with the virus P spectrograph at McDonald Observatory was by Fabricius et al. In 2014, where they also observed that actually even in the centers, globular clusters show some rotation fields. So we were curious about what can the Muse data tell us about rotation in globular clusters. This is the case of Omega Centauri. This is our footprint that we observed, and if you look here to the right, this is the map of the mean velocity that we measured across the cluster center. And we can actually here clearly confirm a rotation signal because the velocities are of the order of 10 kilometers lower in this part than in this part. This is the velocity dispersion map that you see here. And if you look at it as a function of distance to the cluster center, you see here the rotation profile and that it increases as we move further away from the cluster center. And here you see the velocity dispersion profile, where we basically have the decline towards the outskirts of this cluster and then a plateau, but there seems to be some increase, and I'll come back to that maybe later. But there's also some clusters that don't rotate, like NGC 6441, which is a massive cluster near the center of the Milky Way. And here you basically do not see any gradient in velocity over the center. So this cluster doesn't seem to show any rotation whatsoever. And if you do this for all of the 25 clusters that we've studied so far, we only studied 22 in this study, we actually see that most of them show some significant rotation. What we did is that we measured lambda r, which is kind of a proxy for the angular momentum of a globular cluster. And if we plot this, if we then plot angular momentum as a function of distance to the cluster center, you see that we have some clusters which don't show any angular momentum, so those are those down here, and then a lot of clusters which show significant angular momentum. So for 13 out of the 22 clusters, we find very significant rotation in the cluster center. What we also observe is that the rotation usually increases as we move further away from the cluster center, which is also expected from models of rotating globular clusters. The nice thing is then, if we compare the angular momentum of a globular cluster to its ellipticity, there seems to be kind of a rough trend in that more elliptical clusters also have a higher angular momentum. And this is actually a nice agreement with the study of Fabricius et al. That I just mentioned to you a few minutes ago. But do we actually expect globular clusters to rotate? Well, to this, let's make a small excursus to cluster evolution, to cluster formation. In the hydrodynamical simulations that are these days performed to explore the birth of massive star clusters, rotation is actually commonly observed. For example, this is from a study by Mappelli et al. In 2017, where they found that in their collapsing gas clouds, the clusters are actually born with some net rotation. And also we observe rotation in young massive clusters, like in this study of a central cluster in the Tarantula Nebula in the Large Magellanic Cloud. So it's not that unexpected that globular clusters rotate. But I told you at the beginning of the talk, globular clusters know how to relax. And relaxation actually leads to the transportation of angular momentum from the center to the outskirts of the cluster. Now, as the clusters move in the tidal field of the Milky Way, stars in the outskirts are usually at some point stripped away from the cluster. And with them, the angular momentum would be stripped away. And the nice thing about this Muse study is that we actually observe that clusters with longer relaxation times show stronger rotation than clusters with short relaxation times, which actually directly would confirm this scenario that globular clusters are born with some rotation, which gets then via relaxation and tidal forces stripped from the cluster at some point in their lifetime. One nice thing that I will want to study in the future is that I told you about these multiple populations that we observe in globular clusters. And with Muse in combination with HST photometry, we're actually able to to split up our kinematic samples by population and then, for instance, study the rotation fields of the individual populations separately. And there's predictions that depending on which scenario you prefer, you either expect one population to rotate faster or slower than the other. So I think that's a very nice way one can go in the future. And then the second aspect of globular cluster kinematics I want to highlight is about intermediate mass black holes and about black holes in clusters in general. So you've heard in the talk by Vivian yesterday already that we observe a tight correlation in galaxies between the masses of the supermassive black holes and fundamental properties of the bulges around them. Like in this case, I show you the relation between the velocity dispersion of the bulges and the masses of the supermassive black holes. Now, and one question that we still haven't answered is what were the seeds for those supermassive black holes and how did they actually assemble their masses? And if we assume that, since supermassive black holes have these super high masses, they must have gotten there somewhere. And one idea for getting the seeds of those supermassive black holes is, for instance, that they form via runaway merging in young, dense clusters. So if you just formed a very massive cluster, which still has very massive short-lived stars in it, relaxation again might lead to kind of a very fast relaxation. So you have a very fast relaxation of the stars, the massive stars in the center of the cluster, which then would lead to them merging into a supermassive star, which would then collapse into an intermediate mass black hole with a mass of the order of 10 to the 3, 10 to the 4 solar masses. What's interesting is if you just take these black hole mass bulge relations and extrapolate them to the properties of globular clusters, like a velocity dispersion of 10 kilometers per second, you actually also arrive at masses of black holes with the order of 10 to the 3, 10 to the 4 solar masses. So globular clusters are kind of obvious candidates to look for lower mass black holes that might be the seeds for those supermassive black holes. The problem is that so far the results are very controversial, and whenever somebody said, I found one, there was another person saying, no, you didn't. So to give you an idea of the difficulties involved in there, in one study by Eva Noyola, they actually showed that it's actually not so clear where to look. For instance, Omega Centauri, the most massive globular cluster in our Milky Way, doesn't have a very well-defined center. It's rather flat in its central part, and whether you put the center here or a few arc seconds north or a few arc seconds east actually makes a big difference about the results that you get for an intermediate mass black hole. But then even if we look at less complicated globular clusters, we have issues, and we have to ask ourselves, do we understand our measurements? One controversial case is the globular cluster NGC 6388, where two measurements have been obtained, one being down here, so with a velocity dispersion of 13 kilometers per second, and one finding 23. And obviously that's a big difference, and I think Eva has a very strong opinion on who of those is right. But I won't go into further detail, just saying that this obviously is an issue if we don't really, or if we get contradicting measurements. One cluster that we studied with Muse for looking for an intermediate mass black hole was NGC 6397. So we got our velocity dispersion curve and then created models for the velocity dispersion without a black hole and with several black hole masses. And you see that this curve really nicely matches to the models which have a black hole of the order of 600 solar masses. So did we finally find one? Unfortunately, I think we didn't. Because the problem is that NGC 6397 is actually a core collapse globular cluster. And if you talk to a theoretician about it, he'll tell you there's no way you can form an intermediate mass black hole in a cluster that's already core collapsed. Because the intermediate mass black hole would basically effectively delay core collapse until eternity. So those things don't match. And if we have core collapse, we know that a lot of relaxation has already happened in the globular cluster. Now, as I told you, relaxation moves massive objects to the center of the cluster. The most massive objects in globular cluster, however, we don't see because they are stellar remnants like neutron stars. And if we actually put our kind of a central component of neutron stars into our models, as I've done here with different radii of these central components, then we see that a kind of a dense central accumulation of neutron stars can describe the data equally well. So unfortunately, no black hole in here. However, this Muse data actually gives us a really rich data set to search for intermediate mass black holes in a lot of other clusters. And when we looked through the data, we actually found one black hole about which we are quite certain. And to tell you more about this, I want to, the end of my talk, mention that we also do binary studies with Muse. So we don't only observe the clusters once, but we observe them at several epochs and then look for radial velocity variable stars. And this is the globular cluster NGC 3201. This is a Hertzsprung-Russell diagram that we created from our spectra plotting effective temperature against surface gravity. And all the stars colored in blue here are those for which we observe radial velocity variations, like this blue straggler here. If you look at the radial velocity that we observed over time, you can see a clear variation here. And in this cluster, we found one peculiar star, which in the HST images doesn't look any kind of interesting. And also, if you look at its position in the color magnitude diagram, it's like basically a normal turn-off star. However, if you look at its radial velocity curve, it shows huge variations of the order of 150 kilometers per second over time. And then if you compare this to a Keplerian orbit, you basically find that it must orbit around an unseen companion. And from the solution of the Keplerian orbit shown here in red, we get a minimum mass of this companion of 4.4 solar masses. And something with 4.4 solar masses basically can only be a stellar mass black hole inside the globular cluster. But why is it actually interesting to find, or do we actually expect to find a black hole inside a globular cluster? After all, globular clusters must have contained massive stars at some point. So they should have been created in huge numbers. But again, we have to worry about relaxation. And actually, stellar mass black holes might just be a bit too much relaxing, since they are much heavier than the surviving stars. So the mass ratio is of the order of 4.1 or even higher. And what can happen then is that basically you have something which is called the Spitzer instability, which was predicted by Lyman Spitzer in 1969, that basically you have very rapid and very strong mass segregation of all the black holes to the center of the cluster, where they then form a subsystem of objects that's decoupled from the rest of the cluster kinematics. And what then happens is that the interactions between the black holes start kicking out one black hole after the other, until at some point you're basically left with only one black hole in the cluster. And this was supposed to happen very fast. But there have been radio and X-ray observations that suggested that accreting black holes exist in globular clusters. And our detection, to my knowledge, is so far the first detached black hole that doesn't show any X-ray or radio detection in a globular cluster. And showing that those objects exist in the centers of the clusters also makes globular clusters then very good candidates for gravitational wave emission and detection. Because to have a merger between two stellar mass black holes, you need a very dense environment in which they evolve. And then I've also mentioned gravitational waves in my talk, so I can come to my conclusions. And I hope I could convince you that globular clusters are intriguing objects and that they may be old, but that relaxation keeps them dynamic. So that's basically coming back to the beginning of my talk. That's, I think, why we should relax sometimes. And investigating how they relax, however, is quite challenging, but we're actually starting to get all the data to study those processes in great detail. And then I thank you for your attention.
Okay, it's working. Hello. Having a lot of trouble. Sorry. All right, questions? All right, starting over here.
So forever and ever I've been asked, what if you have a bunch of binaries in your Globular cluster? How does that affect your dispersion measurements? I think that you have the data to answer exactly that question. Have you estimated that? Like if you take in around your binaries, what does your dispersion?
So we did some estimations for 3201, so this cluster where we actually have an estimate of the binary fraction, and it's for this cluster, so it has a velocity dispersion of the order of 5 kilometers per second in the center, and I think it goes up to 6 if we don't ignore the binaries. So it's not a big effect, but it's measurable. So it's right.
So I love your data, and I can't wait to get my hands on this.
So we've published all the radial profiles, and, but
So I want to ask about the modeling. What has been maintained for the last 20 years is, I think, the dynamical modeling has lagged quite a bit in the observation compared to the data. Because this data is so nice right now. The models that have been used are very biased, and effectively everything that theorists have told us about these things have been wrong. And I'm not trying to bias yourself by whether it's a core gloves or not. So I'd like you to talk a bit about these models that you are comparing to, and if it's just Baumgart's models or not. And one thing that's very important is a lot of the assumptions that are going into the initial conditions of the models. That pretty much will determine a lot of the outcome there. And so just talk a bit about the models that you use.
So for the case of 6397, we basically used the simplest models that we could get our hands on. So those were isotropic genes models without any rotation, and also like in the very first efforts, we assumed a constant mass to light ratio, which of course for a relaxed globular cluster doesn't make terribly much sense. And that's also why we thought that for the publication that I showed in the end, we don't want to do those simple models since they don't do justice to the data. But we currently don't have the manpower for using more advanced models. So, and I'd be happy for any help in proper models that do justice to the data. So, yeah.
Okay, any more questions?
I just was going to ask Carl, the comment had to do with how many fibers on this guy does the head-dex have?
35,000.
35,000, right?
Yeah.
And how does that compare with the spectrograph you used?
So the just counting the numbers, so each Muse data cube approximately has 90,000. So they're quite comparable. What's the biggest difference between Muse and Virus is that the spatial sampling for Muse is much lower. So, and I'd be very curious to see some data cubes of globular clusters observed with Virus, especially if they have some.
Why for time? I mean,
Yeah.
I'd love to see that too.
Yeah.
So Frank, a comment on that, I speak to the use of people, Andreas and the company, and we had a joke about who's the largest. So on the sky, for sure, we have the largest aerial cover. So Virus is the biggest in the world, and it's even the biggest in Texas.
Do you have any other questions? Do you want to get one more? Go ahead.
One comment on Omega Sen, I really like the rotation profile there of 10 kilometers per second. If we go back to the And in reference to the paper that Ava had on Omega Sun, there's a big difference between what we get and what the HST people get for proper motion. And our argument has been a lot of it is in the rotation because they have to take out any rotation from the measure.
Yeah.
Proper motion. It's just keep that in mind as we go along that the proper motion is phenomenal, but it's very hard to get the solid body rotation out of it.
Exactly, yes. That's,
Okay, with that, let's talk Dr. Sebastian Kamann one more time.